Good morning, everyone. Thanks for coming. We are very happy to have Brian Smith coming to us today. I've known Brian for quite a long time. We were discussing that earlier today when we first met, quite a while ago. So, Brian did his undergraduate work at Gustavus Adolphus College, and then did his graduate work at University of Oregon, I guess with Mike Raymer, probably, right? And then did a postdoc at University of Oxford. And then went for a couple of years, to Singapore, then went back to Oxford as a faculty, and then came in 2016 to Oregon.
Yes,
as a faculty. And so since I'm noticing a pattern that it's Oregon and then go away and then back to Oregon and then Oxford, then go away and then back to Oxford. So I predict that now you're going to be going to Singapore next as your as your next role. So yeah, Brian's been doing always very interesting things in quantum optics and is going to tell us today about also interesting things on enhanced telescopes and imaging. And then also tomorrow is giving the eye optics seminar at 11 o'clock. Right, and so if you're interested, you can see that young man who's waving his hand wildly to come talk to him about a totally different topic,
yeah.
Spectrally entangled photons. So happy to turn things over to you. Thanks.
Great. Thank you, Paul, for the introduction and the invitation. It's great to be here giving a talk in person. So I'm just trying to adjust the mic here. Whisper. I'm going to get feedback. All right. There. Is that better? Worse? Okay. All right. So I'm going to tell you today. Actually, I have to talk really quietly. I turn this off. How is that? I feel like, so poor John, anyone know John Dowling? He didn't need a mic either. So I'm going to turn that off. If you need me to use it, let me know. I have the Zoom. Yeah. Okay. Great. Yeah. So I'm Brian Smith at the University of Oregon currently, and I've been around a little bit now, and I'd like to tell you today about a great project that actually Paul got us interested in quite a few years ago now. Through this project funded by NSF on quantum-enhanced telescopes. I'm going to call it quantum-enhanced interferometric imaging because we haven't really done telescopes just yet. That's where we're aiming to go with this. And so here are the folks at Oregon who've been working on this project in the lab. And here are our collaborators here at Illinois, Michigan, and now Andrew Jordan at Chapman. Come on. Here we go. Okay, so some of you in the audience might remember when I was a postdoc, we started out one of our annual Christmas meetings with guess whose fringes these are? Right? Because in science, and in particular in quantum optics or quantum information, you always end up measuring wiggles, right? Fringes with respect to something you're twisting a knob in the lab. And in this case, the fringes belong to these two individuals, Matt Brown and Marcus Allgeier. So Matt is a graduate student who's been working on this project, and Marcus is a postdoc who's recently departed to a better place, that is NIST. So he's going to spend the summer at NIST and then take up a faculty job at, perhaps a better place if you like lots of snow. He's going to take up a faculty position at the University of North Dakota at the end of the year. So, yay, living the dream. So the problem I want to talk to you about today is that of imaging. So let's define what we mean by imaging. So this is a quantum technologies group, so perhaps we have to go back and explain a little bit of what optics speak is for some. So imaging means determining the intensity distribution of an object. So here we've got, say, 2 point sources, and we're going to try to image them a distance r away, so some range r here. And imaging means this, we want to understand the intensity distribution. So for 2-point objects, A and B, that are some separation x apart, the intensity would be something like IA, the intensity of A, times a delta function, some distance. Let's put little x at the center here. So we've got x plus big X over 2 and x minus little x over 2. So we've got delta functions. These are point sources, and they have perhaps relative brightness I, A and IB. So your total intensity in the plane of the object is this thing here. And so an imaging system is a set of lenses that we collect light with, and we try to reconstruct some image here by focusing the light to 2 points. So if you're really far away from these two objects, then really what you can think of is the light coming in is essentially a plane wave. Right? That's coming in from object A, it's a plane wave coming in, and object B is a plane wave coming in at a different angle. So they have some angular separation, theta. Now, what does a lens do to a plane wave? It will focus it to a point-ish. And the size of that point is given by what we call the diffraction limit, right? And so you might have, in your, I guess, first or second year physics courses, for those in physics, you would have taken a class and you have this idea, this thing called the Rayleigh limit for a circular aperture, 1.22 lambda over d. Right? Now 1.22 just comes from the fact that you have a circle. So you get something that's a spot, right? And so you're limited to the separation between these two. So if I want to measure the separation, right, the distance apart these two are, so another way to think of what a lens does is it maps angle to position in the focal plane. So different angles will map to different positions here. And the minimum angle that we can resolve, or separation of angles, is given by this Rayleigh criteria, where as we bring these two closer and closer together, these blobs are going to start to overlap. And the width of those blobs is given by the wavelength of the light divided by the diameter of the lens and multiplied by the focal length of the lens. That's the physical distance here. So the angular resolution that we can resolve is lambda over d. All right, and this is often called the Rayleigh limit or the diffraction limit. So in order to get better resolution, look at smaller and smaller features, we want a bigger telescope. Right? That's the result of this. Bigger means better in terms of resolution. Also, one other additional point is that bigger also collects more light. And that's important because we get more photons. And we're going to look at a case where we're in what you might call a photon-starved regime, where we're looking at very distant objects. They're very faint. And so we want to collect as much light as possible. So a bigger aperture is going to be better for us. Okay, so let's look at some of the what you might consider smallest features that we've looked at. So this is the image of the supermassive black hole at the center of the Milky Way galaxy that came out last year from the Event Horizon Telescope project. And these observations have achieved a resolution better than 60 microarc seconds. So I'm not an astronomer. I don't know what a microarc second is. I have to convert into radians. That's 3 times 10 to the minus 10 radians. Very small angles that they can resolve with this. So if you think about it, this is equivalent to the size of an orange on the moon observed from the Earth. So if you put an orange on the moon and you try to look at that orange, they can resolve that orange. They can just resolve an orange on the moon. It's insane, right? It's amazing, fantastic. So for the wavelength of observation, which is about a millimeter for these radio telescopes. That means a lens with a diameter. So we'll take the wavelength here, lambda. So we got, basically we take that theta, lambda over d, and we solve for d in this case. So we've got lambda over the angle. So you get about 3,000 kilometers is the effective diameter, right? So did they really build a 3,000 kilometer aperture for radio waves? No. So, you know, it's effectively the lens the size of a continent, though. So really what they did, how did they create this image with this resolution? Well, they combined radio telescope signals from multiple radio telescopes all over the globe. So you can actually go and look on the Event Horizon Telescope webpage. They have this great little picture. So each one of these is a radio telescope, even one up here in Greenland, where they can collect data from each of these different radio telescopes, but they have to collect it in a coherent way, right? So each radio telescope measures both the amplitude, right? So how bright the light is, but also the phase, right? So if you go back to this image here, right, what you're measuring, you have wave fronts coming in, and another wave front coming in, and they're interfering, and then they form these images over here. So here's a little picture to demonstrate how you coherently measuring the amplitude and phase gives you angle. Okay? So suppose we have a distant point source and you don't know where it is in the sky. Right? And you want to determine, you know, it's really far away. I couldn't draw a picture large enough, but it's very far away so that when the light comes in, it's essentially a plane wave. And the light, when I say light, this could be radio waves, whatever the radiation is. But you have essentially plane waves now coming in. And when they hit this radio telescope, right, you can think of these as the wave fronts oscillating. So this wave hits here, but that wave has to travel additional distance, and it picks up extra phase going along here before it reaches the second radio telescope. So if you can measure the phase difference between the signals at these two radio telescopes, that will tell you the angle at which the light comes in. It's just like the reverse of if these were two point sources and they emitted coherently, you can emit light in a direction, in a particular direction. It's similar to also what happens with a diffraction grating or Young's double slit, in reverse though. Not the emission, but the receiving of the signal. Okay? So if we can coherently measure the amplitude and the phase, really it's the phase now that's the killer, so that will give us angle. This is also called synthetic apertures, right? So you could imagine if you had a large lens and you just put apertures on either side, it's still going to give you some information about the image, right? But now you're going to have these two apertures that cut out a lot of the light from the lens. So that's effectively what we're doing. So we have to coherently measure the field somehow at both A and B, not just the intensity. So this is not a new concept, and it was actually used, I can't say 100 years ago, but 103 years ago now, by Michelson and Peace to measure the diameter of another star, in this case, Betelgeuse. So they used an interferometer of about 2 meters separation, where they had two apertures or two collection apertures about 2 meters apart. And then they scanned the distance between them to measure relative phases. And were able to then measure the diameter of this object. So some math. How do we go from measuring interference, like phase, and amplitude, to measuring diameters? How does that work? So there's something called the van Sittert-Zernike theorem from classical optics. So how do you determine the spatial distribution of a star? From the fringe visibility as a function of the position of these two telescope stations. So here we've got our object, you propagate some distance z, and you have some separation between your telescopes, your collection lenses. And you vary that distance delta y. So if you interfere them directly, here at a beam splitter, and you look at fringe visibility, so we're going to vary the phase here, delta is the relative phase between the two telescope arms, and then we just look at how much intensity comes out either side of the beam splitter. Right? So think of this as basically it's a giant interferometer. You have a source, you get two beams, and then you interfere those two beams again. And that gives you a relative phase between these two arms of your interferometer. And that relative phase tells you about angle coming in. Right. So if you measure that intensity at the detectors, say one of these, you're going to get the intensity due to y1, intensity due to y2, plus twice the real part of the cross term. Yay. This thing contains phase information about these two sources. And so the van Sittert-Zernike theorem, right? So measuring interference between these two point sources gives you what's called the mutual coherence function. You can go look up in Borden and Wolf or Mandel and Wolf classical optics text, and it's basically a visibility. So there's some amplitude to it and some phase term. And by making this measurement of the intensity at the output here, you're measuring this. The interference term gives you this degree of coherence. So you go back and you think about now for incoherent light sources, if you propagate far, far away from that incoherent source, you get plane waves here that are coming in, and those plane waves are nearly coherent, right? So in terms of the spatial content. So each point is going to end up as a plane wave coming in across here. And there's no fixed phase relationship between the light emitted at one point or another along this source because it's an incoherent light source. It's a star or it's a planet or some other thing. So if you propagate the fields far away and then you look at the coherence functions at these points, so this is where I'm going to sweep a bunch of stuff under the rug. Basically, the Fourier transform of this degree of coherence gives you something like the intensity in the far field over here. Right, so that's the math magic that goes on, is that for incoherent light sources, if you Fourier transform the incoherent light source, you get the visibility that you measure here, or vice versa. You Fourier transform this, you're going to get the intensity in the far field. Yes? Yep. So we use that phase to pick out this visibility. So we control that phase in the lab, that delta, and we use it to basically, you see these things don't depend on delta, and this one does. So we can take a Fourier transform with respect to delta in a data analysis to pull out just this term. And then we get rid of the delta to give us this, basically twice the real part of this thing now. And that's the thing we call J, which is normalized by the intensities of each object. Right. So we can, going from here to there, we do some data analysis, basically. So this is what you measure in the lab. You massage this by but we can control delta. And so we Fourier transform with respect to delta. These end up as peaks at 0. And these are side terms that we can filter out. And then inverse Fourier transform back, and you're just left with this thing. And you divide out by that delta. Yeah. Okay? Yeah. Yes. So, well, when you say timing, what do you mean by the timing? Yeah. Yeah. Yes. There are several time scales that you have to worry about, especially if this is astronomical observations. So you need to have enough time to take data before the atmosphere fluctuates, is one time scale. And that determines how bright objects are. That gives you a data rate at which you can hope to, yeah. So we haven't done those yet. Astronomers work on that. Our collaborator, John Monnier, does. And he's helping us figure out how best we can do this with our single photon sources. And then if you think of, so I'm bringing these two together, so there's a time delay as well between the two, and so you have to account for that time delay, which is a path length difference, not just a phase offset, but a path length difference, and you do have to keep track of that as well. Yes. Okay. Any other questions? Great. Okay, so what is the state of the art in what is called very long baseline interferometry, VLBI? So I told you about the radio telescopes. The radio telescopes don't have to bring the signals together and interfere them. They can measure the field directly, and I'll tell you how they do that in a little bit. However, optically, we cannot measure the field directly in a local way. Right? We can only measure the intensity because the field oscillations go so fast. Right? We cannot track the actual oscillations of the field. But at microwaves oscillate much slower in time, and so we can measure those things very precisely, and we can measure the amplitude. Yes? I will. Okay, so with low noise. Yes, so the challenge is with low noise. Yes, you can directly measure using a local oscillator, and I will talk about that in a minute. Yeah. So the state of the art for low noise, so this is for low flux, right, that you're trying to measure, and that's where the challenge comes in, is the Chara array. So I can't remember what Chara stands for now. So this is in Mount Wilson, down in Southern California. So they have these individual telescope stations here, and these two blue dots as well. And then there are vacuum lines that run from these telescope stations to a central node where they can interfere the fields directly. Right? So just like I have here, they collect at two different telescopes, and then they channel the light from the star down to a beam splitter and interfere them. Right? And the current resolution is on the order of milli-arc seconds, and the long-term goal would be to reach micro-arc seconds. So here's our collaborator, John, literally on an optical table where they interfere these lines coming in from the telescope stations. And so the state of the art for visible wavelengths is approximately milli-arc second resolution for relatively bright stars. So the Chara is the best resolution they have. And the resolution currently, so the separation here is about a few hundred meters in baseline. So the imaging that they achieve here, you have limits due to shot noise in a local oscillator, if you want to do it that way. Signal loss, so if you want to bring signals from tens of kilometers apart, you'd have to use optical fibers. You can't make a 10-kilometer vacuum tube to connect these two. I mean, you possibly could, but I don't think we're going to convince NSF just yet. And then you have turbulence and brightness of objects. So turbulence of the atmosphere and the brightness of the objects. So currently we're limited to about a few hundred meters. And it's difficult to go beyond 1 kilometer. So how do we envision doing this? So the goal for us has been to look at ways to develop very long baseline interferometry schemes in the visible to attain superior performance using quantum ideas. And we'll tell you what that is in a moment. The long-term target would be micro arc-second resolution, so we need to go basically 1,000 times larger, so we're talking tens of kilometers to 100 kilometers separation. So why visible? Well, that's where, so the microwaves are great, but it doesn't tell you everything about astronomical objects. So it contains information about chemistry that's going on. It tells you about planets' atmospheres. It also tells you a resolution of things like exoplanets. It's more difficult because these things don't emit many microwaves. Then you're looking for things that are very dim in that regime. So you're looking for reflections basically off of those. You can resolve black holes in the optical, and that would give you different information than you get from the microwave regime. And the same goes for planet-forming disks and the surfaces of stars. And that tells you about the dynamics that happen on the stars. This particular star that was imaged, the idea here was that this thing is rotating so fast that it actually turns into egg-shaped rather than spherical. And that was they were only able to achieve this through better spatial resolution. So the main impediment that we have to overcome is optical loss. You cannot just bring the light from the telescopes together. That is the challenge, right? Or shot noise, which Brian, you mentioned, and I'll get to in just a second, of detection. So if you want to locally measure these things in a phase-sensitive way, that becomes a challenge when your local oscillator that you're trying to interfere has shot noise. Okay, so the interferometric imaging techniques are broken down into sort of a couple of different ways. So one is direct interference, where you bring the fields together. So you collect starlight. Here's our two telescopes. You collect the light and then send them together, and you see either spatial fringes, or you just interfere them on a beam splitter and you get some intensity fringes. Great, with a phase modulator. So that's the Michelson approach. And then there's this thing called heterodyne or homodyne detection, which is done in radio astronomy. So the way that the radio astronomers locally measure the electric field is to interfere the light you collect with what we call a local oscillator. So it's a reference field. And that reference, think of it as a coherent state. It's like a laser, or in the case of RF, it's a maser. Right? So it's a constant field that you can interfere with this other thing, and you get beat notes if they're not the same frequency. And that gives you phase information about the field that's coming in. So the problem doing that with very weak signals coming from your star on the order of single photons is that the local oscillator that you use, if it's a laser, has uncertainty in the number of photons there. And so when you do, you interfere your collected single photon or maybe 2 photons from your star, you interfere that with a laser, then you're going to have noise on your detection due to the uncertainty in the photon number of your reference field. And that noise is what causes a problem when you're looking at very weak objects. So the signal to noise that you get if you try to do this homodyne or heterodyne is the main challenge. So you might ask, there's another approach which is called intensity interferometry. And intensity interferometry is great. This is known as Hanbury, Brown, and Twiss. And the challenge there is it requires more star photons. So we're focused on what we call a weak regime, where we have on the order of a single photon. So intensity interferometry is ruled out by the brightness of the objects we're trying to observe. So some theory work done probably now 10 years ago, or just over, showed that direct interference, bringing the two beams directly together, is optimal. gives you the most information about the object that you're trying to look at. So if you could do this, great. If you can't, well, you could try to measure the fields using this classical local oscillator, but you run into a problem with shot noise. So as you attenuate down your sources, so the brightness of the source gets low, then this becomes a problem. Right? Your signal to noise washes out, and you're no longer able to gain information because of your local oscillator. So ideally, what we want is a non-classical state. We need quantum here. And this is what was proposed by Gottesman, Jennewein, and Croak right around the same time that Menkes-Tseng came up with this theory. And the idea was to use a quantum reference. Yep. No, it's not just measurement time, it's measurement per mode, right? So there's certain number of modes that are coming in per unit time. All the atmospheric fluctuations, that's just an overall rate. But if you're looking at very dim objects on the order of 1 photon or less per mode, then you're in trouble.
That mode is something.
Doesn't matter, it's a mode.
Okay, but
Well, it's not just per second because you're interfering it with, you're looking at one mode at a time. You have to demux everything out into certain modes. And you could either do that into time bins, but then you also have frequency as well. And you can only tile time and frequency. You can do it either with long photons that are narrow in frequency or broad photons that are narrow in time. And it's just the occupation per mode is very small. So when you interfere, each mode is only going to interfere with one of your, your reference is also single mode. And that's where you run into problems. So the local oscillator still has that shot noise per mode. Because the Planck distribution, basically the noise per photon, right, h bar omega is small. So the energy, if you think about on average, you're getting a certain amount of energy from the star per unit time. That's your intensity. And the shot noise, or you get more photons from your star in the RF than you do in the visible. Yeah, you have a stronger field amplitude yeah. And the shot noise is more because a single photon costs more in the visible than in the RF. Yeah, so there's more electric field. It's not as discretized in that. And this was known by Towns quite a while ago, and that's why RF does so well with this. But in the optical, you pay the price, the shot noise per photon, right? The energy, it's what kills you. Yeah. So the basic idea now, the quantum comes to the rescue by introducing a reference that has essentially no shot noise. So how do we have no shot noise in a reference? Well, shot noise corresponds to the uncertainty in the number of photons that you have in your reference field. So let's use a single photon state as our reference. There's no uncertainty in the number of photons that you have, and therefore no shot noise. And that was the idea proposed by Gottesman, Jennewein, and Croak. And so the idea is to utilize what we call single particle entanglement, right? So what the idea is you take your single photon source and hit a beam splitter. Now you have these two modes in a superposition state. So you have the left mode going here, has no photon, and the right mode has a photon. Oh, and I've got my phase offset on the wrong side. Well, it's relative phase, so that should be a minus then. All right, so the other side goes with, you either have a photon on the right and nothing on the left, or vice versa. But it contains relative phase information. This state, which you could call an entangled state of the modes, contains phase information about the relative phase between the two. Now, if you have a single photon that comes from your object that you're trying to image, and it's going to go to one of your two telescope stations, and you look at coincidence events across these two. So a coincidence between DR1 and DL1, well, you had to have a single photon from the Earth and a single photon from your star. You don't know which side came from the star and which one came from the Earth one. So you add the two probability amplitudes coherently for that event, and you then take the modulus squared. That gives you an interference term that contains the relative phase. So we'll sweep all of that under the rug. I won't go through the math. I'll just say that the probability for coincidence counts you can calculate. If you have a single photon coming from the star, single photon from the Earth, after this beam splitter, you get this visibility again. That's one of the technical challenges. Yes. So you have to be able to, you have to have data that you collect fast enough before the phase drifts here. Yeah. And that's one of the key challenges we're trying to overcome. Well, it's the rate at which atmospheric turbulence changes and its coherence area. Oh, the fiber, yeah. So that's also a challenge, but that's less of a challenge. You can control the relative phases there because you can send reference beams and you can measure. Yeah, that will lead to noise, right? Because it's not interfering with the local oscillator. So this single photon is in a single mode, and it's only going to interfere with the same mode coming from the star. Yeah.
You actually start.
So there's a long story to that. Yeah. And I'll try to get to it towards the end, where that's not what we've done. This is just a proof of concept, and where we're headed, I'll tell you in a little bit. Okay, so you might have also noticed that I'm just throwing loss. Instead of why don't you just bring the light together here at this beam splitter, right? And forget interfering with our local oscillator. Well, the idea is that we want to distribute this single photon to the two telescopes and then interfere the starlight with that and make coincidence measurements. But you're going to lose rates just because now if you want these to be really far apart, that single photon has to propagate a long distance, right? And as in this picture, so you get this exponential fiber loss. How do you overcome that? Well, if only we had a way to share entanglement between two distant places. Oh, well, we'll just ask Psychot Gua to help us out with the quantum internet in the future. So we're going to sweep that away for now and rely on the quantum internet that's going to come to us in a future near you. So it's going to require being able to distribute entanglement over long distances, right? It's the same problem. But this may be the first application of an actual quantum internet, right? If you're really thinking about distributing quantum entanglement over large distances, what are you going to use it for? You're not going to use it to do Eckert protocol for QKD. What are you really going to do? Distributed quantum computing over, between two sides of a continent? We think this is probably one of the more interesting applications and perhaps one of the first early uses of a quantum internet, if there is such a thing, to ever come out. Okay, so assuming now we have everything distributed, let's tell you what I've really done in the lab so far, or rather what Matt's done. So we produce heralded single photons using good old parametric down conversion, where we get a click in a detector here, it heralds a single photon. We send that to a beam splitter off to our two telescopes, and then we use the same laser to generate our effective starlight. We generate that light by hitting a diffuser that moves in time to randomize and give us incoherence spatially along the wavefront. So we have an incoherent wavefront here now after this rotating diffuser, and the light just spills out, and we go through an aperture, and that acts as our object. Right? So we have a speckle pattern in the far field that looks something like this to show that we have pseudothermal light. So here's another picture of that. Our Ti sapphire goes through to generate our photon pairs, and this acts as our non-local oscillator here. So the source we're using is at wavelength of 800 nanometers, roughly, from Peter Moseley. And we then send that to our two telescope stations. So the telescopes are really, I think we have a picture of it here. I'm trying to remember in the next slide. And our phase delta is modulated in time, so we know exactly what it is at any given instance. And what we measure are coincidence events between telescope A and telescope B, right? So what we do is we go through our aperture. I think I have this in the wrong order. So we go through the diffuser, then the aperture, and then propagate a long distance to a beam splitter to separate the fields, and we collect into single mode fibers. Right, so and then we interfere. The interference happens on fiber-based beam splitters here to our two detectors. And those detectors are nanowire detectors that have about 50 picoseconds timing resolution, so very tight timing resolution. And we get clicks, and we know what the phases are. So we measure now as a function of the telescope position, so we can move this telescope collection up and down relative to this one, or I guess I'm moving this one in this picture, delta Y. So we have double slits that we've been measuring. So that's the intensity pattern that we want to reconstruct. Here's a picture of our diffuser and the rotator. Very complex. All right, so one of the challenges, I think, Ophir, you mentioned was, hey, what about the phase? And that's been one issue in the lab, is that we have a random phase here in our fibers. And that causes a problem if we don't get enough data over the time fluctuations of that thing. So what you end up measuring then, instead of, we have this randomized phase in our visibility then, and now that allows us not to measure the visibility, but the visibility squared. So we miss the phase term in the visibility. And that causes us then, when we take this Fourier transform, to not reconstruct the intensity distribution, but the autocorrelation of the intensity. That's because it's V squared, not V. So that's what we measure, is currently the autocorrelation for our double slits. And so this is our data. So this is the measured visibility as a function of separation of our two telescopes. Notice this is length scales of millimeters, but our telescope apertures are microns, right? So these are single mode fibers that we're collecting into, and we're scanning those single mode fibers with respect to one another. And so we get these two autocorrelations when we do Fourier transforms, the data analysis of this. So what we've shown so far is that using a single photon non-local oscillator, we can reconstruct effectively images of distant objects. So in the lab with a fake star. Okay. Now, one other thing that we've done is look at signal to noise. And so here on the left is our quantum single photon local oscillator. So this is our heralded single photon, and this is on the right, our classical local oscillator. So this is unheralded down conversion, which effectively, so we use the unheralded down conversion because it's mode matched to what we had originally for the heralded down conversion. And we see a decrease in the signal to noise, significant decrease in those two, for the same number of data points. Now, we get a lot more data rate for the unheralded version though, and so there's this trade-off between signal to noise versus data rate. So you actually get much more data in this case, which is a problem that we have to solve. Another problem that, so we have lots of things yet to do. So hooray, quantum sort of works. But to actually deploy this thing and look at real sources, there's lots of things to happen. So one example is we are generating, so this is frequency and time. And starlight is randomly occupying, so each of these blobs you can think of as a single spectral mode that's captured from the star at a given time. So at any given time, one of these frequency channels could fire, and we don't know which one, which means at every time slot, we have to have a single photon prepared in all of these frequency channels. So we have to do some multiplexing at all of these time slots, and then look at lots of demultiplexed signals. So that's going to be our phase 2 project. One of our phase 2 projects is trying to do this spectral and temporal multiplexing. Right? So that's one big challenge that needs to be overcome. And obviously another, well, there's several problems involved in that, but the other big problem is getting things that are really, truly distant from one another. And that's going to require a lot of work. So next steps, we're planning to move to telecom wavelengths, increasing the baseline separation that way. And also it turns out to reduce atmospheric turbulence. We are moving towards an experimental demonstration with the sun and Betelgeuse. We'll use initially single photons again in a single mode, and then move to this multiplexed version. The long term though, we're talking 10 years or more, probably much more than that, would be quantum networks in order to distribute the entanglement that you're going to need on the 1,000-kilometer distance or greater. Okay, so we've shown a proof of concept that at least with heralded single photons as a non-local oscillator, we can image objects interferometrically using this scanning approach. With improvements in the phase, phase stability of our two paths, we'll be able to get the intensity, not just the intensity autocorrelation. And we can increase the visibility per coincidence event with this heralded single photon rather than looking at what we call a classical local oscillator. So the challenges are going to higher rates to actually implement this thing on a telescope. And here's our list of, we need heralded single photons, better detectors, and show this thing with true thermal light sources. Okay, so that's the group at Oregon and the folks that have done the work on this project, the rest of the group in Oregon now. And we're looking for postdocs and PhD students, which are in high demand these days. So I'll thank you and take additional questions.
No, thanks, and thanks for leaving us plenty of time for discussion and questions.
So, I guess I'm trying to think of a...
I guess, is there like an optimal...
No, so the weird thing about starlight is there's no unique modal decomposition for light from stars.
Okay.
And so you can pick whatever modes you want, and you're going to get essentially the same overlap. There's a nice paper from Eggy Branchik and John Sipe that go through and talk about the mode decomposition of thermal light. And it turns out there's no unique decomposition, which that's not surprising. And so you can pick whatever you like. So here we've chosen to tile in little blobs like this, but you could look at long time slices with narrow spectral bins as well, as long as they're Fourier transform limit. Right.
John.
That's correct.
Now that we have a
So I think we looked at that. I'm trying to remember. I don't think there is a significant, so you're thinking like in terms of a noon state. Yeah, and I think the problem is that the information that you're trying to gain is from a single star photon, and it's the relative phase essentially between those two paths. And so the information is carried in the single excitation coming from the star, and what you're trying to do is just extract the phase between those two. And I can't remember why n photons does not increase the phase. I'm thinking we had looked at this with one of Andrew Jordan's folks, and I don't remember why that was the case, but I seem to recall it wasn't advantageous.
At the very least, if you have loss getting from the source to the thing, then it becomes more sensitive to loss in that case. It's hard to keep noon states alive. The questions?
I mean, that's sure. I guess or you just go to telecom and distribute, and then when you get to your base stations, you frequency convert those into the many channels that you want. I guess trying to think of you'd need 1,000 kilometers of hollow core fiber. Yeah, that becomes a big challenge too. So I'm thinking telecom's the way to go.
I think it's also more lossy than telecom fiber, right? Even though it's not supposed to be. But well, it's supposed to be. But other questions? I'm gonna ask one question. So I'm afraid it'll probably be a hard one. So we know that with the issue of turbulence. Let me go back. With our laboratories, sometimes if you have a lot of temperature fluctuations in your laboratory, you just take the data from whatever, those 2 hours in the middle of the night when the temperature is stable. And so similarly, if you've got atmospheric turbulence coming in, you could imagine, well, I'm only going to wait until I happen to have a time bin that didn't have a lot of turbulence, and I can measure my thing there. And I don't know which time bin that is, so I'll measure a whole bunch of them, and then I'll see the one that had the biggest visibility, and then that will be the thing that I'll say was the visibility of the source. I'm wondering if, now going back to, if instead I have local oscillators and we're worried about shot noise, I'm wondering if there's a similar sort of post-selection you could do where you only take the events where there happen to have not been as much shot noise coming from the local oscillator in that particular event.
I mean, so I don't know the answer. However, my initial thought would be that, anytime you filter out your data, you're throwing away information. And I guess in these rare, thinking if the events are rare, then you're probably not going to win.
Well, I guess that's also true. That's right.
So
because you don't have many stellar photons to begin with. So if you're going to only collect even a smaller fraction, that's probably true.
Then I think cherry picking isn't going to win in that case.
Okay. Well, let us thank our speaker again.